Okay. In the why Alessandro, our speaker, joins to the call, let me introduce myself. I'm Zoltán Varjú. I'm the organizer of the Hungarian Natural Language Processing Meetup. And I'd like to thank to the London Text Analytics Meetup and the Budapest Neo4j Meetup that they advertised our event, and I welcome their members too. And I'd like to thank to our sponsor, Crow Intelligence, to support the meetup. And also, I'd like to thank Manning Publishing to introduce us to Alessandro because we know him via Manning. Me and my colleague Orsolya, we are working with Manning. We are developing LIP projects, and Alessandro is writing a book on graph-powered machine learning for Manning. And also Alessandro is a chief scientist at Graph Aware. And okay, why others are joining to the call. Let me tell you a few words about our meetup. We started 8 years ago in Budapest, and due to the COVID situation, we started our online sessions with help of other natural language processing meetups across the globe. And usually we have one meetup a month. We are organizing the next one. We are not sure about its exact time, but it will be about using NLP in the legal field. And okay, I think almost everyone who's registered joined to the call as I see the numbers. So I'd like to ask Alessandro to start his talk. So the stage is yours, Alessandro.
Thanks a lot. Can you hear me okay, right? Just checking. Can you hear me?
Just write into the chat, guys, if you hear Alessandro.
Okay, I think that, I mean, my microphone says that you should be able to hear me. So, good afternoon. My name is Alessandro Negro, and I am the GraphAware's chief scientist. And thanks for the introduction. So the reason I'm here today is to show you how to better understand or even predict your customer needs, current or future, improve the quality of your products, or save costs for your company, as well as increase their revenue. And I'll show you how all these goals can be achieved, not without a magic trick, but using the knowledge that you already have in your organization. But currently, this knowledge is locked away, since it is in the form of data or information in multiple databases, so distributed in multiple databases, in pile of documents and procedures. And of course, it is in the mind of your employees. And in this way, it is totally useless. In order to unlock such knowledge, access to it, and use it for those purposes, it is required, first of all, a mental shift. From classical approaches such as data warehouse, business intelligence, or search engines, and migrate to a new and proper organization of such knowledge. In order to understand the mental path required for such a shift, and recognizing the value behind the knowledge which is already providing your organization, but is still not used properly, let's consider a concrete scenario. Let's start with a simple example. Something that even though you are working with or you are struggling with in a different domain, it will resonate in your head because you are dealing with, most probably, with the same type of issues. So suppose that you are the VP of product or the CEO of a manufacturing company producing any type of goods, for example, cars, medicines, toys, whatever, and you would like to improve the product's quality, reduce the maintenance costs, make your customers happier, or you would like to optimize the production chain or production costs by limiting the issues along the entire production chain. So in this case, most probably, these are some of the few questions that you could ask yourself, or that you are actually keep asking yourself. And these questions are just a small set of all the possible, but they are crucial, they are critical, since the way in which you will answer to them, the actions that you will take accordingly, can determine if your organization will succeed or will fail. And moreover, these kind of questions cannot be answered looking at a pie chart, a colored pie chart, or performing some search queries. You need to create, in this case, a proper knowledge framework based on the data and information that you already have, from which you can distill useful insights to take the right actions in the right direction, actually. So in this case, where will you start? Where will you find the information necessary to take the right decisions? Well, I'm sure, and I'm sure since this is true for 100% of the organizations, from the guy selling fruits on the market, or up to the big multinational company, that you are collecting data, a lot of data actually. And I'm not referring only to numerical data such as purchase orders, transactions, but also data in other formats, such as shift notes from the production chain, or reviews from your customers, or complaints from your resellers, product descriptions, documentation, whatever. But these data, and specifically these textual data, are not used properly right now. How can you take these data and convert them in something that concretely helps you to spot issues or to identify margin for improvement? Well, the process can be summarized in this image. Some of you may have seen it before in different shape, in different format, because it generally it shows the path from the simple data up to the wisdom. In this case, I projected it also to simulation. But let's start the story from the beginning. The data in its native form is completely useless because it doesn't provide any value. It is sparse, distributed, and in most of the cases, it is unstructured. So it is chaotic. To make sense of data, we have to transform it, organize it, and this process produces information. However, for the information to become knowledge, that is what we are looking for, which is learned, requires more work, a lot of more work. Knowledge is by definition connected information, and there is a big jump between, or let's say, from information to knowledge. It's a quality change, but it's not an easy change. It requires a transformation process which, by connecting dots, creates sense, significance, and meaning from the information. So transforming information in knowledge is where a lot of companies are currently struggling with, because they recognize the value behind the knowledge and are actively working to perform this conversion, because insights and wisdom are just above knowledge. So they aim to identify meaningful piece of information in this knowledge and relate them to each other using, for instance, cause and effect relationships, similarities or dissimilarities, and so on and so forth. But insights and wisdom, once obtained, gained from connected data, actually in this case, provide a guidance on producing better products, making users happier, reducing costs, or delivering new set of services. In this scenario, simulations allow you to, let's say, project the knowledge that you have about your reality right now in the future, predicting, actually, considering multiple scenarios, the consequence of possible choices that you are taking right now, or that you could take right now. So this is then an image of a journey, a complex and long journey, actually. But the pot of gold at the end of this rainbow, definitely worth all the effort. But in order to follow such process, it's clearly important to understand the difference between such an approach, such a journey based on knowledge, that has knowledge in the middle of this journey, and other traditional approaches, such as, for example, data warehouse approach. You know, because this is one of the most classical approach, I will say. As you may know very well, data warehouses are central repositories which consolidate data from a variety of data sources and set the foundation for business intelligence. And business intelligence, or BI, if we prefer, is built on top of this data warehouse and provide a set of tools that are used for accessing and exploring data to better understand how the business is performing and make, in theory, better informed decisions that could improve performances or create new strategic opportunity for growth. But it is supposed here that by using this concept of key performance indicators, or KPIs, in a colored dashboard, like this one in this case is, a CEO or a VP of product have all the information necessary to take the right decisions. Is it true? Well, of course it's not. For a lot of reasons, actually. First of all, data warehouses aggregate data coming from one or multiple transactional processes, accounting, purchase orders, and so on. So in the business intelligence, we are considering only numerical data. But in this way, a part of the story, actually a Greek part of the story, is totally lost. It's totally ignored, since a lot of data sources containing just text are totally out of this approach. Moreover, data warehouse stores aggregate data in some way through this concept of dimensions, not single event. That means that if we have a few bunch of events, very significant, but that are, let's say, happening for a small amount of time, actually, they will never be revealed in this approach, because once we aggregate it, we will lose this detail. And finally, KPIs and charts are sometimes very hard to understand. And it is hard definitely to put them together to relate to two different KPIs, because it's sometimes very, very hard. So in summary, we can say that data warehouse and business intelligence together that enable the so-called data-driven decision process are not enough. For one specific reason, I will say, of course, in addition to what we have discussed just so far, that is the knowledge. Where is the knowledge in these approaches? How can I use such dashboards, even colored dashboards, to answer my questions, such as, why is this happening? Why are my customers complaining every single day? Where is the issue in their production chain? Of course, I cannot just answer to these kind of questions, because what is missing is the knowledge that is not gathered properly because of the missing data, because of the structure of this data, and so on and so forth. So let's try another approach. This is more recent, definitely, than the data warehouse. It is this search engine approach. It is, in theory, and actually in practice, even more advanced. So search engines are tools that can store huge amount of documents, providing a fast search access to them. Documents in this case are decomposed in fields of any type, from text to numbers, from date to binary data. So in this way, it allows you to collect any sort of data, not only numerical one, in a more flexible schema, more unstructured schema. This makes, of course, merging a multiple and heterogeneous data into these search engines much simpler, even textual data, of course. So from this perspective, it seems that, you know, the search engines are solving the issues that we were mentioning before. We can process textual data. The unstructured format of these documents allows me to merge different sources without any restriction, like in the case of data warehouse. And even single events can be stored. But still, there are some limitations of this approach, because first of all, I'm still storing isolated documents. So even though it is possible, but the reality is that it's very hard to relate documents in a way in which I can easily query through these relationships in search engines. Furthermore, even though search engines can collect various data sources, still they are delivering in the form of KPIs, data or insights, if we can call them in this way, to the end users. So how can I find common patterns in all of them, in these KPI-based dashboards? It is hard to reveal complex pattern as well as simple pattern in this case. So even in this approach that is called information-driven decision-making process, there is still a big missing part. That is, again, where is the knowledge? Now, okay, I can take all the documents that I have, regardless their nature, and store them in a single repository. But again, there is no connections among the different documents. Even the events that I can store in isolation still are not connected. So I cannot easily identify relationships among these documents, these data sources even more. So I would like to show you a different approach in this case. So let's consider this graph-based approach. And instead of just giving you the answer, I would like you to follow the process. So supposing that in this case, we are a car manufacturing company, and we are constantly receiving these complaints from a specific area about issues with these cars. So in this case, I have just two claims coming from two different resellers, and I would like to store them in the form of a graph. And this is quite simple because I can easily store them in the form of a graph with these nodes representing the claim connected to the product by a relationship where the products are represented again as a node, and the reseller's ID. Then here I can do something more. I can process my textual data, so the content of the claim. And for example, I can recognize that there is a word that is recurring often and often. So that is window broken. So I process my text, recognizing that there is a keyword coming back and forth again and again. And so I can store it as a graph. So as a node, and these two claims are connected to it because they are related to it. So there are the same concept in both of them. Then I can take the production chain information. So the way in which I produced these products, actually. And so here I have the nodes representing something else. So the production chain element that actually brought me to that specific set of products. Then I can access to external source of knowledge. For example, I can get that where are the resellers. So I can find that the one is in San Francisco and the other one is in Los Angeles, again represented as nodes. And then I can know, accessing to ConceptNet 5, for example, that both these cities are in California. So finally, I can add the last piece to the puzzle, that is the supply chain, that is telling me exactly who is providing the raw materials. And so at the end of this journey, that as you can see is quite straightforward, what I can get back is a graph. It's a graph like this, where we have several sources of information coexisting, in which I'm connecting also the dots, as we were speaking about the knowledge, but we will come back on this. Let's try now with this graph to answer to our questions. Why my cars are coming back again and again with the same issue? And actually, and well, let me say that this is based on a concrete example. So I changed some words and something, but the idea has been applied concretely in a real use case. So what I'm saying is something that we proved to work. So in this case, we can notice that there is a yellow node that is a common element in all the issues that we are receiving. So now, if we go a little bit more in deep, we can discover that this supply node is referring to a supplier that is providing these suspensions for these cars that seem to be not fine-tuned enough for the roads of California. So this is causing a lot of stress on the windows that keep failing again and again. So finally, with this approach, we found the answer to our questions. It's not a KPI here. It's not a color dashboard. It's something that concretely is answering to our question. And this is possible because this is not just a graph. It is a knowledge graph where basically, in generic terms, we can say that a knowledge graph is a representational model. It consists of a set of interconnected typed entities and their attributes representing the real world entities, claims, cars, products, whatever, and any relationships among them. So the knowledge graph sits in the middle of this evolutionary path from data to wisdom or to simulation described before, and represents a concrete enabler, not only for advanced analytics, but for real prediction, for real artificial intelligence application. So it is capable of collecting and organizing data from multiple data sources and analyze the results of this aggregation, I would say, providing flexible and extensible access patterns to it. It represents not only the only way to manage the whole of enterprise data in full generality, and it is fully domain agnostic. Hence, it works for any organization. If you are producing cars, like in the example before, or you are renting houses, or you are building apartments, such a graph can help you to understand your business, to understand your customers, to understand your company itself. So that's why major companies such as Google, Yahoo, Facebook, Microsoft have created their own knowledge graphs that empower multiple services such as semantic searches, or and enable smarter processing and delivery of data. So the use of knowledge graphs is now the norm rather than the exception. So why they are so powerful? Well, the knowledge graph approach, compared with the approaches that we have seen so far, or that we mentioned so far, first of all, let's say it allows you not only to store relationships among entities, but sometimes these relationships are created automatically. So you don't need just to, extract relationships and store, but this relationship can be built between data sources coming from a variety of data silos, for example. So, and once you store them in the form of a graph, you have multiple access patterns, because in a graph in general, and more specifically in the knowledge graph, every single node and every single relationship can be your access pattern for the analysis. So knowledge graph can easily store also contextual information. So apart from the above, as in the case of, this information about San Francisco and Los Angeles, they can store contextual information where these things are happening, for example. And that's why they are a concrete enabler for, as I said before, artificial intelligence. And last but not least, you can have even a nice visualization that are, again, totally different than what we had before with the data warehouse or search engine, because storing the data in the graph and then analyzing the data using the same pattern, the same data model, actually is allowing us to make more deep analysis, so that our analysts, our data scientists can not only just crunch this data and get something out, they can go more in deep, they can see the why. So they can give you answer about why your products are failing, even without any machine learning. Then of course you can apply machine learning. And of course we hope so, because this is also the content of my book. But if we would like to take it simple, it's enough to go through the data stored in the graph model to get the answer to your questions. So supposing that I convinced you, what should you do to get started with knowledge graph, actually? Because, of course, I made it very simple, but this is not always the case, because it requires a lot of effort, because you need to extract the hidden structure from the text. You need a model that will allow you to merge easily data coming from different data sources. And then on top of this, once you have this knowledge graph, you would like to perform several types of analysis, and ideally even visualize them properly so that your analysts, your data scientists can access to this data in a proper way to get insights, to get wisdom, and then in theory perform even some simulation like link predictions and this kind of stuff. So what you need actually is a tool like Hume, for example, that I will show you later in the demo. So Graph-Aware Hume is an ecosystem which converts the structured and unstructured data from different distributed data sources or data silos in a single connected source of truth. That is the knowledge graph. And this knowledge graph will represent a new asset for the company, because on top of this, you can then deliver multiple different services to final users. And of course, you will like to visualize. So if we go back to our journey, actually, a platform like Hume can help you to, let's say, is capable of providing solutions and features that cover all the needs in the path of converting data to wisdom. And this will be clear through the example, in which you will see how we can concretely take the data and convert them in a knowledge graph, and then visualize them, perform the analysis on top of this. So a single tool can drive you along the entire journey. And at the end of, you have not only a proper knowledge graph, but also a decision-making system, a decision framework, which helps you to look at it and take the right informed decisions that are exactly the goals that we had at the beginning. So in this scenario, of course, you can see that we can have multiple inputs, and this can be then converted in multiple outputs that could, again, hands in the existing infrastructure that you have. So the integration of this ecosystem is very seamless. And at the core of this infrastructure, there is Neo4j, because Hume is mostly based on this concept of collaborative knowledge graph. And of course, the way in which we store this knowledge graph is critical, is a key element of our infrastructure. Otherwise, we cannot just do anything. So, and that's where Neo4j comes in, because actually it is offering our mechanism for storing this, this knowledge graph. And it allows us, thanks to this flexible data model, to merge data from a variety of data sources, to provide via Cypher, for instance, capabilities for accessing properly this graph as a graph, because Cypher allows you to make the queries specifying what is the access pattern that you would like to do. Of course, once you have it in the form of a graph, you can apply all the libraries already available in knowledge in Neo4j, and we will see a specific example in the demo. And finally, since at some point you have to go in production, it offers all what you need about this. So it is ACID, so you don't have to take care of details about when you are storing to be sure that if it is stored or not. It is scalable, so you can have multiple cores working together to deliver features in stability. I mean, so that if one goes down, you can take the other as a master, and the other replicas will continue to work as expected, and so on and so forth. So it's really for such type of critical, I would say, application in the infrastructure of a big corporation. So let me switch to the demo, and after that we will have some time for the questions. So what I'm doing recently is to try to help the community against the coronavirus spread. You know, so what I did was to start gathering a lot of different data sources. Some of them are available under this Cord19 project that is on Kaggle. That is, you know, quite huge, I would say. Still, you will see I'm using a previous version, but we are going to process the whole of the data in the next iteration, because of course we would like to see how much, at which extent we can push this. So that contains a lot of, I mean, this is purely unstructured data because it contains, you know, papers, the full papers actually. So what we would like to do is to store these metadata related to the papers as structured data, but also the textual data, and merge this data with other sources of knowledge, such as, for example, some other data sources such as Ethernet. That is a database that contains a lot of biomedical knowledge, specifically connection between diseases and genes, or genes and proteins and compounds, and so on and so forth. And another database, and there are other coming, that is called UniProt, in which we have all the proteins information. So imagine this scenario. Imagine that you would like to get this big knowledge graph to the scientists so that they can perform research, perform analysis. And we will see a couple of examples in that sense, actually. So basically, the idea is that what we have to do is, of course, take this data and import in Neo4j, so create our knowledge graph, and then perform some sort of analysis. So in this sense, Hume offers you all what you need. First of all, you can define a schema for your knowledge graph. Actually, you can define even more than one. In this case, I'm showing you a subset of this schema in which we have the papers connected to the body of the content of these papers and the abstracts, and then we have you know, the author that is split in multiple instances, then connected to the author as a single instance. Then we have you know, the other part related to a portion of Ethernet, in which we have the connection between genes and compounds, and we will see what we would like to do with this. Together with all these data that are more or less structured data, we have a lot of unstructured part of processed here. We are capable of extracting from the text the named entities. We are capable of doing this in two different ways. So using the CRF model available in Stanford, so the classical approach, and we can do it with BERT approach. So we are using the Shy-BERT models here for extracting biomedical entities or medical entities out of the text without any supervision from us, but it is supervised, of course. Then we are capable of extracting the keywords in an autonomous way, so without any supervision in this case. And we will see how we can use different approaches for, how to say, recognizing topic, as in the case of LDA, this latent duplicate allocation for extracting topics in a probabilistic way. We will see another example in which we are using a pure graph approach for extracting these topics, and we will see how much of quality, I would say, it is. So what to say? So how you can do this? Orchestra is the component of Hume that allows you to deal with the ingestion part. Please don't call it an ETL, because it does much more. Of course, it allows you to take your data from your data sources and bring in Neo4j in whatever end source you would like to have. But also, and this is done by, for example, by something like this. So in this case, what I'm doing here is that I'm taking the data from my local file system as a file with this file reader, all the JSON files in which you know, these papers have been converted. Then I can convert them in my knowledge graph using, in this case, a Cypher query, which maps the data from their original format in something else. And then I can store them in Neo4j. So in this case, I can select which database I want. And as you can notice, the system allows you to select more than one. So actually, you can use the same for storing in multiple graph databases if you want. It's very simple and straightforward, actually. And then what I'm doing here is, once this structured part is stored, I'm sending everything to a queue where other processes will start. One of these processes are, for example, extract entities. So in this case, if you see here, what we are doing is that we are taking the, how to say, the data coming in, so the text. Actually, not the text. Here we are using just the paper ID, and then we are extracting the text from the, let's say, from the database, since we stored it fully. And then we are using one of the skills that we have that is capable of extracting biological entities from the text. So here we are taking the data. So we already stored in Neo4j. So then we send to a queue. A queue is listened by other processes, and we will see some of them, in which we are saying, okay, let's take these IDs, extract the data that I need from the graph, send this to a skill microservice that is capable of extracting entities and extracting annotation out of it, and then let me store a portion of this. So just the named entities, that is what you have seen before. And then, of course, I can store this in the graph. You are not happy about this, you would like to do BERT, no problem at all. You can use exactly the same approach in BERT. Same queue, but in this case, we would like to use 3 different models in parallel that plus the 2 that we had before are 5 different models in parallel used for extracting entities from our text. And this can scale at the size that you want, because these are microservices that can run in parallel. So you can scale up. So the process of annotating these documents can be parallelized. I mean, considering as an upper bound only the number of cores that you can get out of AWS, for example, or in your organization. And of course, what I would like to mention here is that if, for example, in this case, you don't want to use a ShyBERT, but you have your data scientist or yourself is working on a BERT model, nothing more simple than just, you know, change this link, respect some input and output constraints, but with Flask or these Falcon, it should be quite simple if you are using Python, and with the Spring Boot applications, it should be even easier. You can just get some text. Look at the examples here in which we are just sending text and we are specifying what is the pipeline that we would like to use. And the system is, whatever it's returning will end up in this enriched part. And then with a query, we can just go through this enriched part, extract what we need and store them properly in the graph itself. So, and finally, and then we will see the result of this, I would like to do more. It's not enough. I would like to recognize keywords in this sense. So I need to create a more complex pipeline of work. Let me just reset this one because we updated recently. And what I'm doing here is, again, starting from the same queue. So again, another process on top of the same queue. I'm extracting the information from the database. Again, in this case, I'm just merging together the abstracts and the part of the body. And then I'm still annotating using a different pipeline. So again, this is Stanford-based, but it is using a Stanford pipeline because I needed this annotation part. And then we have a mechanism that is called entity extraction that is based on this text rank algorithm that we slightly improved, considering also type dependencies and this kind of stuff. That is a fully graph-based, that is capable of recognizing keywords in the text in a autonomous way. So I didn't train any model here. So it is purely based on what is capable of, in the capability of the algorithm, actually. So, and then again, I'm storing this data in the graph itself. So let's go to the nicest part, actually, because what I can do is that I can access this data. So let me just clean a bit. So I can, you know, now, I don't know if you remember what was my schema. Here I have the same view, but I have more information because I can get what is the content of this schema. So starting from this, I can, for example, search for the top 20 genes because Hume offers you the capability of defining global and local actions that are predefined access patterns. So if you don't want to write cipher queries or let your customers write cipher queries, what you can do is just writing them for them, write them for them, actually. So in this case, for example, I would like to get the top 20 genes in terms of mentions. So I can just create an action that is called top 20 genes, that is global. That means that it will appear in the search bar. And then I will write the query that is actually doing nothing than just returning the relationships. In this case, I'm doing a little bit more because I'm returning even virtual relationships. And you will see why. Because here, what I can do is to ask the system to show me the top 20 genes that are connected to each other via this mechanism. Because here, this part is the structured part, is the Ethernet part. Here is what we have extracted from the unstructured part. So you can recognize this by, these local actions, because in this case, for this specific part, I can get the top 10 articles mentioning this specific gene, and I will get something like this. But on this other side, what I can do is something even more interesting, because one of the common problems here for coronavirus was to find compounds, so medicines that can help in fighting this disease. So the idea was that, I would like to see if it exists. If it exists a compound that can be used for solving or for mitigating the effects of this coronavirus. So I can click on drug repurposing, and I can see that exists 2 different compounds that are connected to this gene that actually interacts with one of the genes. So this is not mentioned in any of the articles. It's just there, but it is capable of interacting. So even with the 2 jumps, I'm capable of finding compounds that can help me in fighting these genes. So imagine this in the hands of the researchers. Of course, this is an enormous value for them to search through it. As we were mentioning in the case of cars, of course, we are merging different data and we are concretely navigating it. But this is not enough, because I can even do more here. And I can do more combining multiple algorithms here. I will show you just a couple of ideas, because again, I can use, for example, my orchestra to create a sort of a co-occurrence graph, where the co-occurrence graph of keywords is built in this way. You have 2 keywords. They will be connected by this co-occurrence graph if they both are mentioned in the same article. And of course, what I would like to do is that I would like to weight this relationship in a way in which I will take into account how often this is happening. And actually, it's a little bit more complex, because I'm also considering who is dominating this relationship. It appears complex, but thanks to the orchestra, it was just a matter of doing a first query that is doing nothing else than just taking all the keywords that have been extracted before with the orchestra that are appearing more than 5 times in my, because I don't want to get everything here. I would like to focus on the key elements, not just keywords mentioned at one time. And then extracting it in a form of a list, stream the content, because this is streaming actually. And then what just to show you what is coming out from this, I'm just getting the keyword ID and the keyword weight here. I put this observer just for you. And then I'm doing a second query because I would like to stream this process, otherwise it will take too much memory. And then I'm building the knowledge graph, the co-occurrence graph here. So I can show you the result of this again in the visualization. And in this way, I can again create my own global action. It is showing me the top 50 keywords here. So the keywords that are appearing more often, and you can imagine, respiratory syncytial virus. Sorry, I'm not an expert of this. Amino acid, and so on and so forth. Then I can see the co-occurrence graph. Again, with another query that is merging the data already available here, I can show the knowledge graph, in this case, the co-occurrence graph, in which I can recognize clusters of keywords. So in this case, we have, this cluster that, as you can see, it's a cluster because here we are talking about diarrhea. And again, here is the same. And the high mortality rate. Here we have another cluster, and so on and so forth. Now, what we can do is that we would like to use these informations, this co-occurrence graph that is built in this way, so that we can create communities of keywords first, and then communities of papers. So in this case, what we have done was to take this graph, this co-occurrence graph, applying the Louvain algorithm available in the GDS library that will create communities into this co-occurrence graph. And then we were able to extract the keywords in this case. So what I can show you here from the Neo4j, just to show you something more interesting in terms of results. What I can show you here is something that allows you to understand how much powerful is this approach in the way in which you can clusterize these, let's say, these keywords. Let me show you the results. So now I'm getting the top 25 in terms of how often they are mentioned in the text, keywords. And you can easily recognize that these are topics. I did nothing. I just extract the keywords, unsupervised mechanism. I organize them via this co-occurrence graph. I apply Louvain, and now I'm just getting the list of communities with some information about these communities, just mentioning the content of this community. And you can recognize areas. So here we are talking about the viral infections and the related terms. Here we are talking about the Zika virus and the correlationship with this virus. We can go down, so we can see the MERS here, the Middle East Respiratory Syndrome coronavirus. So, and all the related keywords used in the text, and so on and so forth. So it is very, very accurate because it is, extracted from the text. So it's not supervised. This is the thing that I would like to stress out, because it didn't require me to be an expert. So I discovered these clusters after I created this for this demo, actually, because it's not human related. So of course, once I have these clusters that are clusters of keywords, I created a mechanism, again based on query, that will be able to connect these clusters to the papers and create clusters of papers. And again, I don't have to do it by myself, because what I can do is that I can assign topics here via orchestra. So here again, I'm extracting just the list of topics that I created before. And then I can connect papers to these topics, so that I know exactly. And what I wanted to do was to take, not one topic, because what can happen is that you can have multiple topics related to the same paper. And I would like to see in this cluster if there are papers that are connecting both of these clusters. So that was my final, result. That was a system through which I can see, what are the top topics by papers in this case. So I'm just getting the papers, organizing them into clusters actually, and visualize them. So I can, in this case, the top topics are computed by number of papers in the topic itself. So I can recognize different things. For example, this is a cluster, and let me see what it's talking about. So here we are talking about influenza pandemic and pandemic influenza, according to. And if we look at the content, just for from the title, actually, we can see, the content of the title. But in this case, we are not analyzing only the title; we are analyzing even the content. So definitely, the cluster created here is totally relevant. So we are capable of recognizing that all these are related to this specific topic. I can zoom more on another one. So in this case, it's a little bit longer topic because, of course, the length of these keywords could vary according to the Louvain results. So in this case, we are talking about something else. And again, genetic diversity, sequence analysis, genome sequence. So let me just click on some of this. Look at this. So BMC, genomic and evaluation of comparative genome sequencing. So I can have this one also, same stuff, and so on and so forth. So, and as you can notice, there are some papers that could belong to more than one. So this one is belonging to genome sequence, but also to another one that is, let me just see it, that is this spike protein, envelope protein, and so on and so forth. So actually, we were able to clusterize our documents. So imagine now that you have the scientists on the other side that they would like to see, okay, I'm interested in this cluster, and then they can perform some search queries. And of course, this can be done via this search interface. For example, I can search for liver cancer. And the system will be able to give me even the keyword and then connect this keyword to the topic. And then this keyword that is somewhere here can be connected to other, like in this case. Okay, it's trying to reorganize the things. Okay. And so on and so forth. So that's basically the way in which then I can start navigating my graph actually, and extract insights, because for each of these I can continue to navigate, for example, to see what are the, how to say, the terms mentioned into it, and then navigate from there, and so on and so forth. So that's basically the way in which you can then afford where there's a huge amount of data, because we are talking about just for coronavirus papers, 13 gigabytes of papers, actually, not data, just papers that are very hard to navigate. So definitely this opens the way for new type of navigation. So I can show you more, but I would like to stop here because I would like to get more time for questioning and eventually answer to that question.
Okay, Alessandro, thank you very much for your very detailed and deep talk. And yeah, we have questions. First, is there a limit to the amount of nodes of data in a graph database?
Well, practically, there is no limit to the number of nodes and relationships that you can store currently in Neo4j, actually. So, of course, there are some rules in terms of the way in which you are storing them. For example, you should avoid to have dense nodes. That means nodes that have a lot of relationships coming in or out, and other few stuff like this. But practically, you can store as many nodes and relationships you want, actually. So it is limited to the size of your disk.
Cool. Okay, another question. How do you spot low-quality papers so that your graph would contain valid data? Can the graph indicate possibly funny results?
Well, of course, this clustering mechanism can help you to identify a few amount of spot, clusters. For example, in the case of the keyword example, I showed you the top, but of course, if you go down in the list, and we are talking about 605, of course, there are some that has no sense. And then you can start your analysis from this to see exactly what's going on, why they are alone, for example, because here means also that they are even not mentioned, and consider that this is happening after several filters in the meantime. As you've seen, I'm filtering upfront, considering only keywords happening more than 5 times, and still there are clusters that are totally useless with a few papers on it. So definitely this is one of the approaches, but graphs really allow you to perform different type of analysis. This is just an example. You can have many more, actually.
Cool, thanks. Okay, this is an important question. Is there any way to experiment with Hume? I guess they are asking for a free demo or something.
Well, we can definitely demo in different scenarios, in the sense that this coronavirus paper is the most complete because it covers different needs, and that's why we present this in these talks. We can demo for some specific domains if you want, because we have different type of databases. Well, in general, we are also open if we think that the domain is interesting to give some access to the, let's say, to a demo instance of Hume. I mean, let's say, it is not likely that you have to click a button and you will get an instance. We would like to have more control on who is testing the Hume, because of course, it comes with some costs related to the infrastructure. So we would like to know if it's worth the time that we will spend and the costs that we have to sustain to make you able to access to it. But yeah,
Okay,
there is
thanks.
opportunity.
Okay, another question. It seems the schema definition is very important. How do you come up with a good schema, and how difficult is to update, modify it later if you want to?
That's definitely a good question. That's true. A schema can be the big difference from success and failures, actually. There is an advantage in the graph. Unless you are, how to say, summarizing stuff, it's definitely possible to migrate from one schema to the other quite easily because of this schemaless approach available in Neo4j. So at the end of the day, a graph by itself, and that's the way in which Neo4j works, it's made by nodes and relationships. And actually you can shuffle these concepts again and again, converting one schema into another schema, actually. Of course, there are cases in which this is not possible. An example is when you are keeping track of a call, of calls, so let's say between two peoples, and you just summarize with a number how many calls, and you just store one relationship. Of course, you cannot go back and store all the relationships between them. But apart from that case, you can definitely migrate from one schema to the other. What we suggest is that in your paperwork, you should take advantages of this concept that is also expressed in my book, for example, that is related to this Lambda architecture, in which you keep your master data set somewhere else. So just the log of the actions, for example, that you are like to keep track of, and then you use a graph as a real knowledge graph. So you take a portion of this data, clean them, and store them as a knowledge graph where you have to go through the knowledge that you would like to get. If it is wrong, you step back, the master data set is still there, you extract other data and store them again. So you shouldn't be scared about trying and failing. What is different here, and the Hume in this case can help you, is to shorten the time that is passing from when you think to start testing something and when you will fail or succeed, because it will free you up from the hardness of dealing with a lot of details, I will say.
Cool. And the last question, it's a bit theoretical as I see it. Have you ever considered a kind of inverse approach where you'd merge heterogeneous graph data sources into a knowledge graph and then annotate them using NLP for answering natural language questions instead of graph queries? Okay.
Well, definitely possible in the sense that, as I said that when I was presenting the orchestra, it's not an ETL even for this reason. Actually, the graph is definitely part of the journey. But if the journey ends with a graph, it's just up to you. Of course, for example, we have a common, quite a recurring pattern, I would say, in which we use the graphs as a sort of, intelligent system where we store the data, we process them, and we export it in other environments. I have presented some example like CRM and stuff like this, but it can be even search engines, actually. This is very, very common. So we use the knowledge graph for merging data and then exporting multiple views of this knowledge graph for performing some sort of conceptual search. And in that case, we are using Elasticsearch as a really end system in that case. So that's the way in which we can think about having the graph in the middle of a longer path. That's the idea.
Thank you very much, Alessandro. This was our last question, we really appreciate your time, and thank you very much for your
thank you very much
for your thoughts on Hume and knowledge graphs. The meetup has been recorded, and we will publish the video on our YouTube channel. And I think Alessandro will email me the slides.